Good afternoon, everyone. So welcome to this version of Quantum Colloquium. Today we're happy to have on Sachin, who's going to tell us about topological quantum teleportation. Sachin?
Thanks for the introduction. Pleasure to be speaking to you all today. So I'm going to talk about quantum teleportation, like one of the most classic protocols of quantum computing. But I'm going to frame this in the context of annuals. So these are through the quadride particles, which some of you may have heard of before in some previous talks. So I want to talk about how this protocol would manifest in theory of annuals and certain theories of annuals. So let's start with a bit of motivation. All right. Is that complete that cool? All right, so why do we care about annuals and why do we want to control them? Well, if we could control annuals, this is tantamount to being able to do something called topological quantum computing. I'd say, sorry to share that, but just quickly, one of the main problems with building a quantum computer is interference from the environment, and it turns out that annuals have these properties or these states that they span called fusion states. Right, so what you can do is you can encode quantum information in the possible fusion outcomes that some annuals might have. The point is that these fusion states are non-local, so the environment can't interact with these fusion states unless the annuals are localized at a point. So therefore, annuals should provide a robust platform for manipulating quantum information. All right, that sounds great. So what's the experimental state? Are annuals pure fantasy? Well, many people might have argued that they were pure fantasy until recently. Others might have argued total opposite. But the community got together in around 2020, and I think everyone pretty much agreed that there's incontrovertible evidence of abelian annuals, which are found in the 1/3 filling factor of the quantum Hall effect, which is a canonical place to look for annuals. Now, as for non-abelian annuals, which are typically the kind we want to do some quantum computing, their existence is contested. There have been claims, but they're controversial claims. Now, there have been some promising leads recently by Willett et al., looking at the 5/2 and 7/2 filling factors, whatever that is. These are just some type of quantum Hall system. And the types of annuals you'd have in these systems are called Ising annuals. But far from confirmed and still controversial. So just to get across the idea of what an abelian and non-abelian annual is, in brief, if I have two, so you can see I've circled two dots there. These dots are meant to represent annuals. They have some state space H, right? Now, if one of those particles is what we call an abelian annual, abelian there, but okay. If one of them is abelian, then the dimension of that filter space would be one-dimensional, right? And if both of them are what we call non-abelian, that's equivalent to the state space having dimension greater than one. And of course, that's what we want. We want to encode a qubit, for example. We would want two annuals to have a two-dimensional space. All right. So I was talking about these interesting directions pursued by Willett, looking for these things called Ising annuals. Now, Ising annuals, or things that behave like Ising annuals, also manifest in these one-dimensional wires, which realize these things called Kittier chains. And on the end of these wires, you have some excitations called Majorana zero modes. Now, while these aren't things that exist in 2D, rather 1D, they kind of behave and quack like an annual, so think of them as Ising annuals 1. Right. So there have been many claims that people have detected these Majorana zero modes, which would be a non-abelian annual, and there's been quite a few high-profile retractions. So many people might say that there's been a bit of a crisis in the Majorana zero mode community. All right. So from this doubt and uncertainty, it's formed an interesting line espoused, well, at least that I've seen by Steve Simon and Zheng Wang in different places. So the idea is that you shouldn't really believe that someone has a Majorana zero mode, or I guess in general, a non-abelian anion, until you can demonstrate that you really used your would-be quasi-anion to perform some interesting quantum computation. Right. Okay. So with that in mind, we want to come up with. So say we have a would-be excitation. Maybe it's manual, whatever. What are the simplest operations we can perform on this to show that we've moved some quantum information around here, really done something with it? And so the simplest such examples in quantum computing are the super dense coding protocols and the quantum computing protocols. So not only do I want to sort of come up with really simple protocols, or really simple realization of these protocols in this context, I also want to remove the need for braiding. So this is kind of, I'd say it's not work, because the whole point of the anions usually is that you braid them to manipulate the quantum information. So braiding anions is tantamount to performing the quantum gates, right? So the weird thing here is that I'm sort of going to say, well, you can pretty much ignore the braiding structure, and just by doing some other stuff, recoupling these anions, as you'll see, I can realize the protocols. Why might that be a good thing? Well, braiding is typically quite difficult. So what does braiding mean? It means that I'm taking one anion and moving it around some other anions on my flat table. So these are 2D particles. Now, controlling anions, we need some fine degree of engineering control. So you need to engineer a lot of control in the system to move around these microscopic particles in pretty exotic systems. So, in fact, motivated by the same sort of difficulty some years ago, Simon and a group of other people that came up with a scheme called weaving, which meant you could do any topological quantum computation using just one mobile anion in a system, right? So that you don't have to move any of them around, you just move one of them. So, okay, the point is, braiding's hard, it can be messy, but I want to dispense with it altogether. Okay. So yeah, along this direction, I should mention some of the work that's already done. So the first place in the literature you can see we've been talking about teleportation in the context of anions was a paper in 2021 by Huang and Burns, who was at NYU Shanghai, and a bunch of other people. They simulated teleportation using Majorana zero modes, but so what they did, they weren't actually using Majorana zero modes, they simulated a Kitaev chain on a system, superconducting qubits, so they weren't actually using anions. It's a simulated thing. But okay, that's the first place where we can see someone talk about teleportation using Ising anions. Okay, and the second place, sorry, unfortunately seems to have bugged out and I'm missing the author's name, I apologize, but so Zhu and Zhu, last year they put out a paper where they really talk about braiding Ising anions in an algebraic context. So here's a picture of the protocol snapped up in their paper. So the idea here, so time is flowing upwards in their diagrams, and mine will flow the other way, is that you pair create a bunch of particle-antiparticle pairs. Alice wants to send some quantum state to Bob, who might be far away. Half of all of these pairs go to Alice, and Alice wants to send this quantum state 5. She interacts with these pairs sent by a third party, who we'll call Charlie, does some operations on them, makes some measurements, and gets out some qubits, A1, A2, A3, and A4. So the qubits here are the possible fusion outcomes of a pair of Ising anions. Two Ising anions can either fuse to the vacuum, that is, they annihilate, or they'll fuse to what people call a fermion, right? So that's your 0 and 1, your qubit. So A1, A2, A3, and A4 are fusion outcomes. Now, after Alice has made these measurements, she'll send what she's read off over to Bob. And using the bits that Bob receives, he will apply some correction gates, right? He'll do something to his Ising annuals in order to recover the state phi. Okay, so, okay, and then to briefly mention what we're doing in this context. So, like I said, I want to go beyond this. So the first small result was here. There's a lot of braiding throughout the protocol. Small result is that we can actually demote or defer all braiding until the correction step at the end, but I won't talk about that. The other is so there's another protocol, which I'll talk more about in a second, sequence coding, which is equivalent to quantum teleportation in a way. If you can do one, you can usually do the other. So the other was to talk about superdense coding in the context of Ising qubits. Right, but what I think is most interesting is the idea of dispensing with the braiding altogether. So I won't talk about these small advances, but rather I'll talk about the braidless version of these protocols. Okay, so perhaps before going over or recapping some basics about anion algebras, I should say a bit more about the teleportation protocols. So I'm just going to switch my screen here. That's okay. So might stop and or is
It shows on my screen.
Oh, it does. Wait, this?
Another paper shows you.
Oh, okay.
And this club.
Good. Yeah. All right. That's what I want to be showing. Just checking.
But hopefully it shows up here as well. It's showing
Ah,
up.
yeah. Okay. That is a problem, isn't it? Okay. Use the whiteboard instead, but that might mess things up.
Sure. Yeah. If you want.
All right. We'll just do that. All right, so teleportation, I'm going to use the board. Where would it be best? Right.
In the middle.
Right, so without going into too many details, I just want to sort of give a rough idea here by sketching a diagram. So we've got three people. We've got Alice, Charlie, and Bob. Right, so Alice has some state, some qubit even psi, and Charlie, he sends 2 qubits out towards Alice and Bob. All right, but not only are they qubits, they are, the squiggle here, I mean, they're maximally entangled, right? So once these come over to Alice, and this part of the, what you call a bell pair, comes over to Bob, they share a pair of maximally entangled qubits. So Alice takes half of this pair coming in from Charlie, and she might apply some gates, and she performs a measurement on a certain basis. And this results, once you measure your qubits, you get 2 bits out, I and J. So where I and J take values in 0 and 1, right? And on the other hand, Bob, while all this is happening, so at first, if we think about what's happening on Bob's side of the picture, right. So Bob will have what you call a maximally mixed state. If we just look at his part of the system, okay, so he'll have a state which is a perfect mixture So he can't really know what Alice is sending over to him. Right, so this just describes his half, the EPR pair, or the maximally entangled pair. Now, after Alice has performed her operations over here, what Bob ends up with down here is a state Uij of psi, where Uij is some operator that depends on the bits that Alice measured. So the information does pop out on Bob's end, just scrambled according to some bits 0 and 1. So usually if you have ij equals 0 and 0, state size already on Bob's end. And this is where people tend to get a bit confused and they say, oh, you've got faster than light communication. But that's not what's happening here. So really, if you think about Bob's, like the state that Bob has here at the instant that Alice performs measurements on the qubit she wants to send, and her half of the pair from Charlie, Bob actually has an ensemble of states. So I'll explain what I mean by that in a second. Uij psi ij. So sorry, here I have so I'm just got the qubits. So with equal probability, Bob doesn't know what Alice has measured. It could be I or J. So he has an equal probability, he has an equal distribution over the set of states Uij psi, the possible ways in which psi could get scrambled. So it's only once Alice sends these bits over to Bob, and this is the key part. Only once Bob has possession of those bits does he know with certainty which state is in possession of from this ensemble. Right, okay, so there's no faster than light signaling happening here. I should mention that, I will mention that there is one group of church of people, perhaps you could say, who believe that when there's a pair of maximally entangled qubits, there's really, okay, and yeah, take this with a pinch of salt, but there's really a wormhole connecting Alice's location and Bob's location spanned by this qubit. And when Alice performs a measurement, this results in the collapse of the wormhole and the transmission of the state Uij psi through the wormhole. Unfortunately, the bits I and J can't fit through the wormhole at the same time. But again, that's just, it's an interpretation. It's, you know, wild fantasy, but it's, you know, it's what some people believe. So just mentioning that for full color. All right, so all right, so that's teleportation. Hopefully everyone's got a rough idea of what's going on. Right, maybe one thing I say is demonstrate how funky teleportation is as a procedure. So suppose Alice and Bob have pre-shared 2 qubits, and so they've got each got half of their bell there, and Alice wants to send a bit to Bob. So yeah, so Alice wants to send just a bit to Bob, an element of 0 or 1. And there's some malevolent party, Eve, in the middle, who wants to know what Alice is sending Bob. Maybe it's a stream of bits, right? So Alice doesn't want Eve to know what this is. Now, using teleportation, Alice can send her bit to Bob, kind of, all right, this is going to sound weird, without sending it to Bob at all. So once Alice sends these bits from the measurement over to Bob, Bob will know how to correct a state. So beforehand, they've agreed Alice will either want to teleport a state 0 or a state 1 to send 0 or 1. Now, Bob could end up with, so say Alice wants to send 0, Bob could end up with the flip 0, that is the Pauli X applied to 0, or exactly what it was meant to get, 0. He doesn't really know which one of these he's going to get. Now Alice makes a measurement and sends a pair of bits over to Bob, and now Bob knows what to apply to his state in order to recover the bit that Alice wants to send him. But the key point is that these bits which Alice sends to Bob are totally uncorrelated with the secret bit or the state she wants to send, right? So this really demonstrates that these two qubits, you're using work done in the past. They share a correlation, and you can send the bit just using this past correlation. The only information it sends is a totally uncorrelated bit. So I think that's quite remarkable and demonstrates like that teleportation really is a cool thing. And right, okay. So briefly, because I'm aware of the time, the dual idea for teleportation is superdense coding. So right, teleportation, we could express teleportation as this visible. Yeah. Okay, so we can say one entangled bit plus two classical bits does the job of, or suffices to send one qubit. So these are from Bennett's laws, right? And the dual law to this is that one entangled bit, along with sending one qubit, is equivalent to sending, or is capable of sending, two classical bits. So an entangled bit means a bell pair here, two maximally entangled qubits. So you can kind of see there's a symmetry between these two laws. This one's teleportation, and this one's superdense coding. So you can kind of see, you can swap these two around, right? So in the sense, the resources you have for one are all there. It can kind of be re-scrambled to get the other. So that's what I mean by when I say that superdense coding is dual to teleportation. So what is superdense coding? It's what you want to do is encode two classical bits into one qubit using also your resource of your entangled bit, and then you send your entangled bit after like forming some measurement and some operation, you send that over to Bob, and now Bob has the 2-bit classical bits that you wanted to send to him. So it's called superdense coding because, you know, in classical channel theory, if you use a classical channel, you can only send at most a bit at a time. But now we've really left Shannon theory because we're using a quantum channel over which I can send a qubit with some entanglement shared over it. Using these resources, I can, with one use of the channel, send 2 classical bits, hence superdense coding. All right. Right, so, yep.
So in my understanding of teleportation is still very not advanced. So in terms of time gain, in terms of normally in the linear system of things, very, very associated with time, like linear in a linear sense. Assuming where things also linear. But in this sense, what does it mean teleportation? Is it like the high school understanding of teleportation, where you actually, instead of sending the information, Alice sends herself to Bob, but in a non-linear.
Okay, that's an interesting question. Maybe I could say a bit more about that closer to the end, but no, it's not. Right, so the point is, you're not breaking the speed of light barrier, right? So ultimately, temporally, you are bounded by how fast, or Alice, this whole procedure is bounded by how fast she can send these bits to Bob, right? Therefore, ultimately, it's bounded by the speed of light. That's the fastest we can send these bits over to Bob. So what, like the thing which is, again, another remarkable facet of this is if usually this is some unknown state and you want to send this far away, in order to do that, like, okay, first of all, you could say, maybe I could take a copy of that state, that unknown state, and send it all the way to Bob, right? But you can't do that because you have this thing called the no cloning theorem, right? it's not possible to clone an unknown quantum state. So that's out of the window. Next, you could say, okay, well, if I can figure out, if I can write this state, it's alpha 0, some amplitude alpha plus beta 1, right? So just some 2D vector. If I know these amplitudes, perhaps I could just, figure them out somehow, write them down, or create another state and send that over to Bob on Mars. But it turns out, in order to determine these amplitudes, alpha and beta, you would need infinitely many copies of this qubit, an infinite amount of time, right? So why teleportation is remarkable is that in light of all these apparent obstacles, there is a simple procedure to send a completely unknown state over to Bob, just using 2 classical bits and 2 qubits which were pre-shared by Alice and Bob beforehand, right? So, you're manipulating the state space from afar. So something weird is happening, but it's not quite high school teleportation, isn't it? Is that clear thing up a bit? Right. Okay. Right. So now I should talk about anions a bit. So I'm not going to spend too much time on it, but I know we've kind of seen some of the basics before about anion algebras. So yeah, again, I wanted to share my screen. Yeah, as long as it shows up on here.
Another screen? Another?
Yeah, so does it show up on?
It shows on mine, yeah. I'm not sure why it doesn't on yours.
So sorry for the hassle.
Not sure.
I could try stopping the share and then yeah,
let's do it.
yeah, maybe that'll do.
Here you go. Very good. Oops, no. Same. It's stuck on that.
Yeah.
On my laptop works.
Yeah. Okay. Not sure. Yeah, about that. Maybe. Oh, yeah. Yes. So to share and zoom. Yes, and show. All right. Okay. Okay, good.
There you go.
And it's still showing up on Zoom.
All good, yeah.
Okay.
But is it recording now? That's what I'm saying.
Yes.
All right. Sorry about that hiccup again. Okay, so I want to go through some of the basics of the algebraic theory of anions, which will kind of need to make sense of what's to follow. Okay, so in brief, you can think of the theory of anions as a set of labels. So here denoted by L, you can all see my cursor. So the set of labels always contains a special element 0, which corresponds to the vacuum. You can kind of think of this as like some algebraic units under some operation called fusion. Right, so anions can braid, twist, and fuse. So in this talk, we've said we're only sort of concerned with the fusion structure here, so we don't have to care too much about braiding and fusing. Now, 2 anions of charge A and B can fuse together in some fusion channel. So there's a relationship determined by this product on A and B, and it gives you a concatenation of labels in C weighted by some integer coefficients n, a, b, c. Okay, so for example, I could have a times b equals d plus f, right? This is an example of a fusion rule, just ways in which I can combine charges to get sums of charges. And you could think of sum of charges as being, often it corresponds to a superposition of possible outcomes, right? That's what happens physically. Okay, right. And so these fusion coefficients, NABC, defined on all triples A, B, C, and L, they satisfy some symmetries. So first one here, you can swap these indices A and B. This kind of corresponds or encodes the fact that fusing anions doesn't care about the order in which they're fused, right? And the second relation comes from the associativity of fusion, right? So fusion is associative on these labels. And the third one also comes from associativity in a way. And associated to any pair of anions, there's a Hilbert space. So suppose I have two anions A and B. Its state space is all of the different ways in which A and B can fuse to another anion C, where NABC is a non-zero coefficient, right? So follows that the sum of the state space of these two anions would be given by the sum of these fusion coefficients, NABC. Okay, so things to take away from here is that VABC is the fusion Hilbert space of two anions. So you can think of this as being a fusion state here. A and B fused to C. Oh, yeah.
Can I ask maybe? So in this system, the way you use these fusion rules,
Yeah.
What is the actual full state space? What is it? Is it you just take all the species, one dimensional for each, like one vector space for each?
Yeah.
And then it counts for everything, like tensor algebra or what?
Okay, it's a good question. So, for example, here you have, as you called it, one species, right? A and B is restricted to fuse to C here.
Yeah.
But the full fusion space for two anions A and B is the direct sum over C of these spaces V, A, B, C.
Yes.
That's the full state space for a pair of anions A and B.
Yeah. But for this system, the full thing, each might have a billion.
Oh, right. Yeah. So, okay. So, right. I think this might be answered as I scroll down a bit, right? So you're talking about maybe I have 100 anions. What does the state space look like?
Yes.
Right. Okay. So this has a nice tensor decomposition coming from the associativity obeyed by the fusion algebra. Okay. So some highlights here are that you have conservation of charge in a way, so you can kind of think of this as an inner product. You can forget about these labels mu because they label multiplicities, i.e. when NABC is greater than 1. But for now, I'll just assume an anion, two pairs of anion can either fuse to a charge or they don't at all, right? So ignore those Greek indices. Right, so you can think of this as an inner product. So C has to match C dash. The charge must be conserved over this process going from the top to the bottom. Okay, and so Greg was asking about what if I have the state space of perhaps K anions, right? So this is given by, or it can be described, perhaps it's easier to start with 3 anion state space. Okay, so for 3 anions, I would have to sum over all the possible fusion outcomes D there. But if I just restrict to the D sector of the charges A, B, and C, we can decompose the space in 2 different ways. So this decomposition on the left means I'm combining A and B first, and then fusing the outcome with C. And this is just the other way, the other parenthesization of ABC. And okay, so there you've got a description of the 3 anion state space, right? And then to get the full state space of VABC, you direct sum over D. So you can kind of see how this would generalize to an N-anion state space, right? You would hack it up into a parenthesization of the different orders in which you can combine the anions and then direct sum over all the sectors. So Okay. So all right, so I should say that here I have these isomorphism signs, right? So these are two different ways of decomposing the same space. That means that there are transformations between the ways in which I can decompose these spaces. So when I define a fusion order, this defines a parenthesization of the string, or a way in which I picking up the space, also known as a fusion basis. So two fusion bases are related to each other by some unitary so-called F matrix. So you can think of this as a change of basis on the annual space. Okay, and I think we've almost got everything we need. So there are some consistency conditions that these F matrices have to satisfy in order for the theory to be well defined. This guy here is called the pentagon matrix. So it just means that any any different sequence of isomorphisms between two spaces, so if I have two different paths between two spaces, those sequences must agree, right? The maps must match each other. Okay, so the final important thing to mention here is something called the pivotal structure, which is actually important for these protocols. So for a theory of anyons, these things are unitary, and what that means is that you can apply these leg bending maps. So, for example, you have a map here, ABC, and you can see I bend this leg on the left down, and it tells me what my state looks like in the target space after I've bent the leg down. So these leg bending maps, they always exist, and they're isomorphisms, and they're actually also unitary, right? So this is a result of something called the pivotal structure on the category, which always exists because it's unitary. So things are unitary because we're doing quantum mechanics. So basically, there's a bunch of algebraic results that will tell you that these leg bending maps, they always exist and they're unitary. Okay, so it turns out that, I was saying if you have two different paths between the same space, those sequences of maps should agree. So I can apply a sequence of leg bending maps to a space VABC in one way. So you can kind of think of this as this diagram on the left here, where the fusion vertex ABC spirals around by 2 pi, and the path on the right, well, this is like the clockwise spiral. Okay, so in like a 2D graphical calculus, these diagrams aren't obviously equivalent, but what pivotality gives you is the equivalence of these diagrams. It's 2 pi freedom in rotation. And actually, from a physicist's perspective, transforming between this fusion space up here to this fusion space is what you'd call a charge parity time transformation. So you can see all the charges get flipped to their anti-charges. So an anti-charge is given by a label with a bar on top of it. So anti-charge meaning I can bring C and C bar together, and it's possible that it will give you the vacuum, or they'll annihilate it. Right? So, okay. So pivotality kind of encodes the CPT symmetry in a way, or it tells you that under a CPT transformation, the inner product is preserved. Okay.
What is time?
Sorry?
CPT.
Oh, what is time?
Yeah.
Yeah, so this is kind of instead of having A and B fused to C, now C splits to A and B. That's it. Yeah. Okay, great. So it turns out that from this pivotal structure, you can add these wobbly lines, these zigzags here you saw on the rubric talk. So it turns out that if you have an anion A and it follows a zigzag, you can always straighten this line at the cost of some unitary phase, TA. So this is just a phase factor, and that's called the pivotal coefficient. And actually, usually this thing can be gauged away unless the anion is its own antiparticle, in which case it's called the Frobenius shear indicator, and you can't gauge it away. It's an actual property of the particle. All right, so with that, I think I will at least get through a bit of the protocol teleportation in the anionic context. All right, so okay, so here I'm saying let C be a unitary braided fusion category, but you should read that as take a theory of anions, okay? And here C is the sets of charges here.
So did you look at the other file?
Oh yeah,
Because that was the other way around.
yeah.
Okay.
I just realised. Okay. Sure. So has that worked? Yes. Right. Okay, good. Right. Okay. So I've got a theory of anions, and what follows, I'll make no apparent use of the braiding structure. So while I want to use the physical jargon, so kind of assume there's a braiding structure in the background, most of what I'm about to say just applies to the straight unitary fusion category. That is to say, you can kind of take the algebraic theory of anions, like I just talked about, but you can strip away the braiding structure and get a more general algebraic algebra. Don't have to worry about that actually. So I'll just, yeah, let's just focus on physical context. Right, so as I said, we'll assume theories are multiplicity free. So that means that if an anion, if two anions A and B can fuse to an anion C, they can only do this in one unique way. There aren't multiple, distinguishable ways in which you could do so. So NABC is always 0 or 1 for any triple ABC. All right, so Alice wants to send a QDIT encoded in the fusion states of A and B. Right, so what does that mean? It means that the fusion state, or the Hilbert space associated to the anions A and B, is d-dimensional. So it's just a superposition over the basis state, the Hilbert space. All the different charges A and B can fuse to, that is. Okay. And so hence a QDIT, if you haven't heard of that before, it's just a qubit, but the DOE version, right? Okay, and right, so we say that the dimension of the fusion space is greater than 1, if and only if, like we said at the start, A and B are non-abelian charges, right? So that's just recapping some things we've already encountered.
Sorry.
Yep. Okay. All right. So there's a graphical calculus, as we've kind of briefly seen, or some string diagram formalism for all this stuff you can do with anion diagrams. So you can always think of the state of an anion as just some coupon, so which lies in the endomorphism space of the two objects. So really, that's just a fancy way of saying, if I have some diagram, kind of imagine that at any slice associated to the objects, there's a state that kind of follows those objects along the diagram. If you don't like thinking that way, you can kind of, instead of that, just stick a coupon on the top side. Both ways are equivalent. They're both the same. All right, so here we have Alice with two anions A and B, and Charlie sends over some other anions, the anti-anions B bar and A bar, and they annihilate at points V1 and V2. And Bob gets the other two charges A and B. So I want to know what the quantum state or the fusion state of these two anions over here are. Well, remember that by the pivotal structure possessed by these fusion categories, we can always yank a zigzag straight at the cost of some phase factor. Okay, TA, TB. And we know in quantum mechanics that global phase factors aren't physically meaningful. So we can throw those away. And so essentially, you can yank this whole diagram straight, and it's just the identity operator acting on the state side that you started with. So if you have annihilation at V1 and V2, Bob already ends up with the intended state side. So, of course, since A and B are non-abelian anyons, it's not guaranteed that you'll have annihilation at points V1 and V2, right? So this is kind of just you're clenching and praying. This is pure luck that size ended up over there. If you really want a protocol, a teleportation protocol, you need to be able to handle any exceptions that are thrown, right? So if I have some non-vacuum outcomes at V1 and V2, i.e. the anyons don't annihilate, I need to be able to handle those so that Bob can apply a correction if V1 and V2 aren't the vacuum. Okay. Yeah, just restating things I've said. Yeah, so it's not guaranteed that A and A bar annihilate, B and B bar, so there's a non-zero probability, some non-trivial outcomes there. Handle the exceptions and apply a correction over here, Uij to the -1, if Uij is the scrambling that occurs from a non-zero measurement at V1 and V2. Okay, so this is the idea. We want to kind of use this natural pivotal structure, this flow along the zigzag. We want to be able to yank it straight. We know we can do that if there's annihilation at these vertices, but if there's not annihilation, we want to be able to do something clever, right? So that we can still yank it straight after all. We've applied some correction terms anyway. So it turns out that, or it will turn out that a natural setting for thinking about these things, thinking about teleportation, using the pivotal structure alone, are Tambari and Agami categories. So I want to kind of make these appear naturally rather than just starting with the definition of this category and showing you that teleportation works. Okay, so now I'm assuming that you can see I've got some outcomes J and I at these vertices down here, and I want to be able to handle those errors if J and I are non-zero. Okay, so what I'm going to do is just imagine, cursor doesn't show up. Okay, so the script E is just some process. Any arbitrary process could occur, but ultimately, whatever happens in there, a charge A has to come out of the bottom. Okay, so in order for this diagram to make any sense at all, I need to be sure that if B and B bar fuse to J up there, the error J, then it's guaranteed that A and J will fuse to A. And that so the second condition says that the only thing you can have coming out of this fusion is A. All right, so that's what you need for this diagram to be well defined if we want to handle errors in this way. So for one, it turns out, i.e. if B and B bar fuse to some charge J, and then it's guaranteed that A and J fuse to A, it suffices to say that B is equal to A bar, right? And two, that is the condition that A must absorb J, it's guaranteed to absorb J. That's equivalent to saying that all the fusion outcomes J are abelian charges, right? They're abelian anyons, right? So that's kind of, those are the conditions that just fall out of saying, I want this diagram to be well defined. This is the way I want to naturally handle my errors, but the obstructions to yanking these zigzags straight.
Does abelian here just mean you have only one vector space in the decomposition?
That's it, yeah. So the two anyons together have a 1D fusion space here. Yeah. Right. So restating that, you need some category C, or you need some theory of anyons where there exists a charge A in the theory, such that when I annihilate it with its antipair, A bar, it gives me the sum of some abelian anyons G. Okay, where course, G has to include the trivial objects. Okay, so it turns out that because whenever you have a bunch of abelian anyons, think about it for a second, under the fusion product, they form an abelian group, right? So G is indeed a group under fusion. So the simplest candidate fusion ring, so what I mean by that is a set of fusion rules, like we've seen, at a set of labels L, they are based on fusion rules. The simplest candidate fusion ring is given by what we call the Tambari-Yamagami fusion ring. So that is, you have some special object Q, along with a group G, and Q fusion Q gives you a possible, it gives you a concatenation of all the possible elements in the group G. Okay, so this is the simplest candidate for some theory of anyons where we can handle exceptions the way we want it to. So those are just fusion rules. Do they really give you a theory of anyons, i.e., do they admit a categorification to a fusion category? Just that alone. Well, these guys, Tambari and Yamagami, they proved that those fusion rules do give you a fusion category if and only if the group G is abelian. Okay, so we denote that the resulting category is Ty of G. Also, we want it to be unitary, right? We need a unitary fusion category. Everything needs to have emission in a product in the Hilbert spaces. It turns out that, yep, it's also always guaranteed to be a unitary fusion category because it's nilpotent as a category, so you can deduce that it's unitary. All right, so in our would-be protocol, we're just going to use these charges Q. Is Tambari-Yamagami anyons, as we call them, which is a finite group, and it has cardinality greater than 1. Okay, but also remember when I was talking about quantum teleportation, it's required that pretty much always when Charlie sends these things out to Alice and Bob, they're maximally entangled qubits. So is that happening here? Well, it turns out to be the case. Yeah, if Charlie sends out 2 pairs of anyons QQ and QQ, right? So let's look at a diagram. So up in that top right, Charlie Bear creates QQ and QQ and sends them out to Alice and Bob. And if I look at them in this fusion basis on the right, where I have the 2 Q charges on the left and the 2 Q charges on the right, because those are going out to Alice and Bob, it turns out that that fusion state is maximally entangled. Really convenient, it just works. Okay, so we don't need to pay any attention to the actual proof here. The takeaway point is that you just apply some F matrices to recouple the order in which the anyons fuse, and it shows you that when you look at the possible, or when you look at the resulting fusion state, the amplitudes E to E, they all have magnitude 1 over root D, which tells you that you have a maximally entangled pair of qubits. Okay, just like if you think of Bell state, all of the amplitudes would have magnitude 1 over root 2. Right? Okay, so should speed up, running thin on time here. So the next part is to determine how these exceptions, i.e. non-zero outcomes I and J, scramble Bob's received qubit. So it turns out, so if we look at what's going on here, it's just the same diagram we had before, but now these solid white lines correspond to the Tambari-Yamagami anyons Q, and any blue lines correspond to just these group elements G, which are abelian anyons. Okay, so I just apply some graphical manipulations. So the thing to note is that these are the leg bending operators, so I'm making good use of pivotal structure possessed by the category. And after doing some manipulation of the diagram, I end up with a string diagram where psi is acted on by some coupon uj, some endomorphism, or some operator if you want, which corresponds to this boxed region here, and then also this little stump coming out the bottom I. So everything counteracts what's going on in that purple box and that stump. Then we'll have unscrambled the information that Alice wants to send to Bob. Right. And oh yeah, and this arbitrary process, I'll just take it to be the simplest thing possible. Just that J comes in and fuses straight onto Q, just gets absorbed. Okay, I'm zooming through these so I can get to the punchline. So this is just how you correct the stump. Basically, if you apply the inverse operator, or if you take out a charge I to the -1, say that that stump has charge I, if Bob splits a charge I to the -1 out of the stump, then you can effectively decouple the effect of the stump on Bob's QTS. Right, so it's just to say we can get rid of the stump by Bob doing some splitting on his side. And also there's a result, a non-trivial result, which tells you that you can think of this in terms of our Tambari-Yamagami categories, but it's more general. If you have a diagram of this form where X is some abelian annual, so it splits out one Tambari-Yamagami annual, gets absorbed by the other one, and then it gets spat out here and absorbed onto that side. This kind of ladder operator, visually, a ladder operator is just equal to the identity, so it cancels. So using these two ideas, if you look at like the whole picture, where you have the errors J and I, right, and Bob applies the reverse direction, he reverses the direction of J over there, so he performs some splitting, and he applies this kind of reverse stump we saw. Well, if you yank that zigzag straight, and then you combine, those stumps cancel out, and you can apply that lemma, which says the action of that ladder operator is equal to the identity, you do just get the initial state psi out the bottom. So, using no braiding at all, and just using the graphical calculus for the category, you can show that, yeah, you can teleport a QTS from Alice's location to Bob's location. Right, so that's kind of the essence of how the proof goes. Of course, I didn't mention anything about braiding, but it turns out that the Tambari-Yamagami category admits a braiding, i.e., so for any theory of annuals, the group G is given by Z2 to the n, so all the objects are self-dual. A few minutes to wrap up, is that okay? Yeah. Right, so theory of annuals, G is equal to Z2 to the n. Okay, any attention to that? And so here's just the beautiful generalized version of it, right? So the same thing going on. I'm teleporting the states of n annuals here, starting at the top on Alice's side, coming down to the bottom. You can apply the same graphical trick. I yank the zigzag straight, and once I've yanked it straight, what I'll have is just a bunch of ladders that all cancel out and the stumps cancel out. So just using those lemmas, you can show that whatever state you start with on the top left, you end up with on the bottom right. And so that is what the teleportation procedure looks like. Teleporting, well, here you have n Tambari-Yamagami annuals, and so you would be teleporting about half. Since any two annuals encode one qubit, you'd have floor n over 2 qubits teleporters here. Okay? And yeah, those orange lines represent the classical transmission of the DIT, right? The DRE bit that Alice has to send over to Bob so he can reply his correction step. Okay. Right, so we've done it, no braiding required. a few points to make here. So we've shown you can do teleportation, no braiding for an infinite family of annual theories. But for the simplest case, when you have n is equal to 1, this corresponds to the Ising theories, right? So the Ising annuals, or the Majorana zero modes, are just the simplest example of this tower of families for which we've shown teleportation works. No braiding required. There's a caveat as to measurement though, right? I haven't said how measurement works. So there's two approaches. One is to bring annuals close together, and so you localize them and then you observe maybe their joint energy or the force between them. And that helps you determine what their total charge is or what their fusion channel is. There's an illustration of it there. And the other is to use some sort of interferometry. So you have some region of unknown charge, you might fire some probe annuals around that region, and using the interferometry patterns, I try and deduce the charge of the annual in that region. So of course we want a protocol where no braiding is required. So we do assume that we have a system where you can just like use some observable, e.g. like the energy of two annuals and the force between them to distinguish their fusion channel. We don't want to use interferometry to do our measurements. As an aside, it turns out interferometry can be done perfectly with just one probe annual for the Ising model, and I wrote the details up on the webpage if anyone's interested in that. Skip over this stuff. Basically, all this says is that instead of Bob applying some correction step where he pulls one annual, so at the top you can see what we had in the protocol is that Bob will pull some abelian annual out of Tambari Yamagami annual and it gets absorbed into the other side. If you don't want to do that, instead you can pair create two abelian annuals and move them apart. So you don't have to do any splittings, you can just kind of use this alternative approach instead. Okay. Sorry. Another thing to briefly mention, because I'm running out of time, summarising the results here, is that in the Ising case, these operators which you saw appearing in the teleportation procedure, they act as the Pauli gates, right? And I would guess that for the higher Tambari and Yamagami theories, these morphisms appearing in teleportation procedure act as elements of the M Pauli group. So you have a braidless realization of the Pauli gates for Ising annuals, which is also cool. So this is the final slide or two, and basically it's showing the dual works, super dense coding. And so kind of the cool takeaway point here is that the proof is actually very easy. That's what it looks like. It's quite whimsical. You just like apply some leg bending operators and it just follows from this kind of conservation of charge property. If you want to share this lemma or in a product structure, right, it proves that if Alice wants to send some bits I and J to Bob, then the bits that Bob measures over here, they have to be I and J. That's just how the proof goes. So much simpler than teleportation. This is the last slide. So as I said at the start, these procedures are dual, right? There's a duality between these two procedures. And the nice thing here is that you can see this duality in pictures by a jigsaw shuffle. So if I look at the world line diagram, so on the left I've got the diagram for teleportation, for super dense coding, and on the right I have it for teleportation, the braid-free procedures. You can see that you can make one out of the other just by taking a section of it and jigsaw shuffling it around. So you can see the duality, incarnate here in pictorial form. So for example, you've got this operator over here that shows up over there. This guy over here shows up over there instead. And the creation of the two entangled qubits, that stays at the top. So it's just one diagram to jigsaw shuffling with the other. So yeah, that comes out really naturally here. I think we'll leave it there. Sorry for running a bit over.
Good, Sachin. Any questions for Sachin?
Can I ask this one quick question? When Charlie speaks, when Charlie says this, does it matter, do they have to be identifying phase and amplitude? Because in that summation where Alice sounds like A with an A bar, I would have expected if the phase is exactly opposite of the line, but it's getting sounds to the and then that comes out, it never completely.
Yeah, I mean, so you shouldn't think of the individual anions themselves as having any phases associated to them. But any phases you have lie in the fusion state of the pair. So don't think of phase associated to just one individual anion alone.
The question?
How does Bob know which eye to?
Yeah,
So Jay kind of goes off the diagram, so I believe you maybe measure it and do something. The eye on the left,
are we looking in here?
yeah,
Okay, so how does Bob know which item?
Yeah.
Okay, so what I haven't drawn on here is that, so this is the teleportation diagram. So really there should be an arrow. As soon as Alice measures I, she sends that dit or dearie bit over to Bob so that he knows what's correct for it. And the same for Jay.
so for I, but the I string sort of joins the diagram again. So is that something we have in you measure I and then, yeah.
Yeah, so kind of I's measured. You can think of the measurement as occurring right there. And then Alice does something else. She's performing not just a measurement, but an operation. So, and that's crucial to like this thing working. So she takes the measurement outcome, that abelian anion I, and fuses it with this leftmost anion here. Right, so yeah, that's what's going on. And kind of the reverse thing happens down here. It's been absorbed over here, and then Bob kind of, when you think of it that way, pulls it back out and sends it to the other side. Yeah. So
There's actually a feature that Alice does there. What actually measures and the outcome is not the abelian. It might be non-abelian sometimes, right? So I think you're just showing the protocol in case Alice happens to measure I, she might measure C, which is not the abelian.
no, so if we go back to, let's say, okay, one of the conditions in this construction of one of my diagrams to be well defined, we'll get there in a second, was that all the summands are abelian charges, right? That's a condition I have here, and that's always guaranteed when I have a Tambari and a Garmi category. So when Q and Q come together, the only possible fusion outcomes are values of the group G, and all of those are abelian anions. They have quantum dimension 1, and that came out sort of, it was motivated naturally in the slide, which I'll never get to. But yeah. So
I see. But do these categories actually have much of a braiding?
yeah, so like I said, so they're always unitary and they're always fusion. For G is abelian, but they only admit a braiding if G is equal to Z2 to the n.
But how can it have a non-symmetric? You mean a non-symmetric? I mean a non-symmetric braiding? How can it be if every fusion is a direct sum of abelian ones? Then the braiding must be symmetric, must it not?
Yeah, I think it might be no, that's not true. It does have. So, for example, Ty. So, do you mean the braiding operators are like square to 1?
Yes.
No, so TYZ2, right? So if I write that out, so I've got the Tambari Amagami object Q and the group elements 0 and 1. So here I have Q times Q equals 0 plus 1. These act in the obvious way, Z2, and Q times 1 equals 1 times Q equals Q. That's the Ising theory. Right, and as we know, the Ising theory has non-trivial braidings.
But if it had, sorry, I don't understand, if it has non-trivial gradings, then there is at least one non-trivial J in fusion.
Right,
I
this-
guess,
Well, yeah, this is a non-trivial. This is like, there's the vacuum outcome, and that's another abelian annual, which could be the fusion outcome. But they're both abelian charges. This is your Eisencubic, right? So yeah, the dimension VQQ is a two-dimensional space. Am I not understanding your question?
I'll need to, let's talk about it.
Yeah, okay, sorry.
Any other questions? Okay, if not, let's thank Sachin again for the very nice talk.
Thank you, Sachin. That was great.
Cheers.